Welcome to ChemFam. Today we are going to discuss a very exam-oriented topic, that is ionization enthalpy, which comes under classification of elements. So what we are going to do is basically we will discuss what exactly ionization enthalpy is. Then we will discuss few important points related to it. Okay. Then we will discuss the factors which affect ionization enthalpy. Okay. Thereafter, we will see the variation of ionization enthalpy in a periodic table. First along the period, then group, and as we do that, we will also discuss various exceptional cases, which is always the case. So let's start. So the definition of ionization enthalpy. What is ionization enthalpy? Ionization enthalpy is the minimum energy required to remove the most loosely bound electron from an isolated gaseous atom so as to convert it into a gaseous cation. So the key words that you need to remember is minimum amount of energy that is required to remove the most loosely bound electron, means the valence electrons, from an isolated gaseous atom to convert it into a gaseous cation. So what exactly happens if suppose your gas is A, all right? So in gaseous state, when it absorbs a minimum amount of energy, which is basically the ionization enthalpy, which is represented by delta IH, it leads to formation of A plus electron, all right? Then there is another term or another name for ionization enthalpy, that is known as ionization potential, which is basically the minimum potential difference that is required where in a discharge tube to remove the most loosely bound electron from an isolated gaseous atom to form its gaseous cation. Now, where is this going to be useful for us? Mostly to solve numerical problems. For that, you need to keep this in mind. All right, clubbed with that, what are the units that we use to express ionization enthalpy? One is electron volts per atom. Next is kilocalories per mole, and the third one is kilojoules per mole. Now, this is the relation between the three units. So you need to remember this. Obviously, we can derive also how this comes. We end up getting this. All right. So this term, ionization potential, and what exactly it is, and the relationship between these three units will help you very much in solving certain types of questions under this topic. So remember that. Then next thing that you need to remember is about the successive ionization enthalpy. When I say successive ionization enthalpy, it means, see, this is the first step, means basically the first electron that is getting removed. So the minimum energy that is required is, to be more precise, delta IH1, the first ionization enthalpy. If suppose this A plus loses one more electron, that is A plus gas, again this time it is the second ionization enthalpy to lose a second electron to form A2 plus gas plus electron. So when this happens, always delta IH2 will be greater than delta IH1. If suppose we have one more step and we end up getting delta IH3 value also, so that will be always greater than delta IH2. That is what you need to remember. And why is that happening? Because as the nucleus or as the atom loses electron, the attraction of the nucleus on the remaining electrons will increase naturally because the number of protons remains the same, right? So the effective nuclear charge on the remaining valence electrons will increase more and more, and therefore more amount of energy would be required to remove the most loosely bound electron. So that's why the successive ionization enthalpy follows this order. All right. Now, let's discuss about the factors which govern the ionization enthalpy. So we will start with the first factor, that is nuclear charge. Okay. So how is this related to ionization enthalpy? As nuclear charge increases, its influence or its attraction over the electron, the valence electron, will increase. So more it is attracted to the nucleus, more energy would be required to remove that valence electron. So that means the ionization enthalpy will also increase. So as nuclear charge increases, ionization enthalpy will also increase. Next factor is atomic size. So as atomic size increases, when atomic size increases, the valence electron, which is in the outermost shell, the distance between the valence electron and the nucleus will also increase. So farther it is, lesser the influence of nucleus on it, and that means lesser the attraction, and therefore it is more easier to remove that loosely bound electron. So less amount of energy would be required to remove it. So basically, as atomic size increases, ionization enthalpy would decrease. Then third factor is penetration effect of electrons. So we all know by now that the penetration effect of s orbital is the highest, followed by p, d, and F and so on, right? So when I say penetration effect means the if suppose an electron is an s orbital and it has highest penetration effect means it has an electron in an s orbital have very high likely probability of being near the nucleus. So being near the nucleus means it will feel more attraction or influence of the nucleus, right? So in that case, more energy would be required to remove it. So I can say when penetration effect of an electron increases, ionization enthalpy would increase, right? So when penetration effect of the electrons increases, ionization enthalpy will also increase. Next is screening effect of inner electrons. So you see, when I say what is screening effect? Basically, the electrons in the inner shell will always always exert a repulsive force on the valence electron. Okay, so there is always a competition between the attraction of the nucleus felt by the outermost electron and the repulsive force felt by the valence electron by the inner electrons. So more the screening effect means more the inner electrons exert repulsive force on the valence electron, it will cancel out a lot more of the attractive force that the nucleus is exerting on the valence electron, and therefore the overall attraction would also decrease, right? So if the overall attraction felt by the valence electron decreases, so automatically it will be easier to remove, right? Means lesser energy would be required to remove that electron. So if the screening effect of the inner electron increases, the ionization enthalpy would decrease. Then finally, the last factor is effect of arrangement of electrons. So either it should be, by now you all would be very comfortable handling the electronic configuration, and at that time you would have seen that half-filled electrons and completely filled electrons have what? Extra stability, right? You would have seen it in case of nitrogen, in case of chromium, right? So so when a species is already in an extra stable state, it won't prefer to disturb that extra stability, right? So then to remove an electron in a half-filled configuration, you would require extra energy, right? And that means higher will be the ionization enthalpy. So as the effect of arrangement of electron, when I say effect, mean the possibility of half-filled or completely filled electron increases, the ionization enthalpy will also increase. All right. So far we have discussed how many factors? First factor, nuclear charge, atomic size, penetration effect, screening effect, and effect of arrangement of electrons. And we have seen how it is correlated to ionization enthalpy. Now, next we will move on to how the ionization enthalpy varies in a periodic table across the period and down the group. Okay, so when we will be discussing those, the factors that we are going to consider is all these factors, and according to various situations some factor will predominate, sometimes another factor will predominate. We will discuss and see the details as we proceed now. So let's see the variation of ionization enthalpy in a period. So we will start with okay, periods. All right, so the general trend, what could be the general trend? So as we move from left to right, what happens? Two things. One is the nuclear charge increases and the atomic size decreases. As nuclear charge increases, ionization enthalpy increases, and as atomic size decreases, again ionization enthalpy increases. So overall, as we move from left to right, ionization enthalpy increases. Now we will see the exceptions in case of period. So the exception number one, we will take second period. All right, within second period we'll see the first exception. Okay, so ideally if we have to follow the general trend, okay, so in case of second period, say the order of ionization enthalpy should be lithium less than beryllium, which would be less than boron, less than carbon, less than nitrogen, less than oxygen, and neon, right? This would be the pattern. But where is the exception? The first exception is beryllium and boron. That is the exception number one. That is beryllium and boron. Let's see their electronic configuration. Beryllium, atomic number 4 is 1s2, 2s2, right? Then boron, it is atomic number 5. The electronic configuration is 1s2, 2s2, 2p1. So here the valence electron is in 2s orbital, and here it is in 2p orbital. So we know that within the same shell, here in this case it is n equals to 2, the penetration effect of S is greater than P, right? So in case of beryllium, your most loosely bound electron is in S, whereas in case of boron, it is in P. And as penetration effect increases, ionization enthalpy also increases. So therefore, what was expected was beryllium less than boron. But what the reality is, beryllium is more than boron. Okay, so this is our first exception. Now let's see the second exception. So the second exception within the second period is nitrogen and oxygen. This nitrogen and oxygen. So what did we expect according to the general trend? According to the general trend, it should be nitrogen less than oxygen. Now let's see. Obviously, exception means actually what happens is nitrogen is more than oxygen. And why is that? Let's discuss. So nitrogen means atomic number 7, right? So what is the electronic configuration? 1s2, 2s2, 2p3. And what is oxygen? 2s2, 2p4. What is this? Half-filled electronic configuration, isn't it? I mentioned also nitrogen just in the previous slide. So half-filled means what? Extra stability, right? So extra stability means ionization enthalpy will be higher than expected. So that's why the ionization enthalpy of nitrogen will be more than oxygen. So for the second period, if we have to write the order of ionization enthalpy, it would be lithium, followed by boron, beryllium, carbon, oxygen, nitrogen, fluorine, and neon. All right. The least would be for lithium. The most would be for neon. So this is alkali metal. So that's why highly reactive, and this would be mostly chemically inert. So exceptions are these two. All right. Now let's move on to the next section, that is variation within a group. So first thing that we will discuss is the general trend, how it will vary as we move down the group. So as we move down the group, what happens? The atomic size increases. Atomic size increases means ionization enthalpy decreases. Then as we move down the group, the screening effect will also increase. That implies ionization enthalpy would decrease. But there is a third factor, that is as we move down the group, the nuclear charge will also increase, right? And when nuclear charge increases means ionization enthalpy increases. But in case of groups, as we move down the group, generally the combined effect of atomic size and screening effect, the increase in atomic size and the increase in screening effect, their combined effect outweighs the nuclear charge, and therefore overall as we move down the group, ionization enthalpy would decrease. All right. Now here too we have exceptions. So let's see the exceptions. So the first exception is seen in group number 13. Okay, so the first exception is group 13. Okay, so we will take one by one, we will go. All right. So as we move from boron to aluminium, boron to aluminium. All right. As we move from boron to aluminium, there will be a sharp decrease due to first thing, the size increase. Okay. And the second is the screening effect of 2s and 2p electrons, of 2s and 2p electrons. All right. So it is going according to trend that as we move down the group, the ionization enthalpy would decrease. Then next, as we move from aluminium to gallium, as we move down from aluminium to gallium, what we expect is aluminium should have lesser ionization enthalpy than aluminium. So gallium should have lesser ionization enthalpy than aluminium, but gallium has slightly higher enthalpy than aluminium by around 2 kilojoules per mole. Why is this happening? Because you see, from as we move from aluminium to gallium, the increase in nuclear charges 31 minus 13, that is 18 units. Whereas in case of what to say, uh, boron to what to say, aluminium was just 8 units, right? Here it is now 18 units. Okay, but compared to that, the shielding of 3D electrons is poor. Okay, shielding or screening, you can say screening also, shielding, or let's be quite screening, because you are so far we have used that term, screening of 3D electrons is poor. So what happens is nuclear charge outweighs this increase in size and screening effect, and therefore gallium will have slightly more ionization enthalpy than aluminium. Next, let's move on from gallium to indium. So gallium to indium. Okay, here it is the same, not much variation. Again, a jump of, how much is it? 31, 49. So 49 minus 31, it's about 18 units. Okay, so here the screening effect will overweigh the increase in nuclear charge, because you have the screening of what? 3D, and you see comes here. So the 4D electrons outweigh the increase in nuclear charge, and the general trend will follow. That is, what to say, the gallium will in the ionization enthalpy of indium will be lower than gallium. All right. Then next is from indium to thallium. So from indium to thallium, what happens here? You see the jump in nuclear charge is huge again. 49, 81. You see, is 32 units. Again a big jump. Whereas the shielding of 4D, and here the lanthanum is there. So in between here, you have the 4F series, the 4F series in between here, right? So the shielding of 5D, the 4Fs and 5D is poor compared to the level of increase of nuclear charge. So this time the nuclear charge will outweigh the very poor shielding of 4F and 5D electrons, and therefore the ionization enthalpy of thallium would be much greater than that of indium, and rather it would be greater than gallium and aluminium also. Okay, gallium and aluminium also. So overall, this thallium would end up just after boron. So the ionization enthalpy trend for second period, I'm sorry, why did I write second period? Group 13 would be boron will have the highest, followed by thallium. Okay, followed by thallium, then gallium, aluminium, and indium. Okay, so this is the first exception. Now let's see the second exception. So the second exception is for group number 14. It is group 14. So in group 14, see, as the initial flow is as expected according to the general trend. So as we move from carbon to silicon to germanium to tin, it will be as expected according to the trend. As we move down the group, the ionization enthalpy will also decrease. But the exception is here between tin and lead. Okay, here you see for lead, it is coming after the 4F series followed by the 5D series, and the jump in nuclear charge is huge again. Okay, it is again huge. So it is around 32 units with poor screening of 4f and 5d electrons, right? Therefore, this time the nuclear charge will predominate, and therefore lead will have higher ionization enthalpy than tin. So the overall order of ionization enthalpy of 14th group would be carbon, which will be having highest, followed by silicon, germanium, then lead, and then tin. So the exception is happening over here. All right. So this is the exceptional cases. Now, the situation of D block and F block is slightly more complicated. A lot more variations are there, which I will be discussing in D and F block video, which will be coming under the 12th standard syllabus. All right, if you are curious, as I upload that, you are welcome to watch it. So this is an overall trend of ionization enthalpy in a periodic table. Now let's quickly try solving this question and then wrap it up. So let's start. Which one of the following statements is incorrect in relation to ionization enthalpy? So the first option is ionization enthalpy increases for each successive electron. Yes, when they say each successive electron, they are trying to say as we move from left to right in a period. So we know that as we move from left to right in a period, ionization enthalpy increases. So that's a correct statement. So next, the greatest increase in ionization enthalpy is experienced on removal of electron from core noble gas configuration. That's true, because it's a complete configuration, already a stable configuration, and then you remove an electron. The force of attraction, the nucleus will hold on to the electron even more strongly, and therefore it will be the greatest. So that is also a correct statement. Then end of valence electrons is marked by a big jump in ionization enthalpy. Correct, because as the valence electrons ends, you will end up coming at the noble gas configuration, and then the ionization enthalpy would be very high, because in each period noble gas has the highest ionization enthalpy. So the statement is also correct. Then removal of electron from orbital bearing lower n value is easier than from orbital having higher n value. You see, basically they are confusing with the words. Basically they are saying that as we move down the group, the ionization enthalpy increases, because see, as we move down the group, for each element the n value increases, n1, n equal to 1, n equal to 2, n equal to 3. So what is happening? The shell number is increasing. As the shell number increases, what happens? The distance between the nucleus and the valence electron increases. The z effective felt by the or the attraction of the nucleus felt by the outermost electron will decrease, and therefore ionization enthalpy will decrease. So the statement is wrong, right? So you have to basically identify the incorrect statement. So this is the answer. So I hope this video was useful for you. I will discuss a lot more questions on this topic in the form of shorts. If you are interested or interested in revising this topic, you can always watch that. So see you soon in the next video.